I'm going to talk about edge colorings today. So we've been coloring vertices of graphs, but you can color edges just the same. And there's some interesting theorems to be made here as well. So let's just give a definition. It's very simple though. So an edge coloring of G is an assignment of colors. I mean, these are technically being defined, but it's just a function assigning labels to the edges, to edges of G such that incident edges get different colors. Okay. Incident edges are edges that share a vertex. Okay, so just maybe a couple simple examples here. So you have like 4 cycle with another edge here. If I want to give an edge coloring of this, I can color this 1 and 2, but this cross edge here can't be 1 or 2 because the edge sees both colors 1 and 2. So say 3. This could be 2 again, and this could be 1 again. Or you can color a path. 1, 2, 1, 2. Okay, maybe a more interesting example, since both of these actually have the same ordinary chromatic number, and this one will illustrate something useful for us in a moment here. Like a star, for instance. Normally, you only need 2 vertex colors to color this, one for the central vertex and a second for all the outside ones. But here you need a different edge color for each of them because all the edges touch all other edges, right? 1, 2, 3, 4, 5, 6. They all share that central vertex there. So I needed 6 colors for this guy here. Okay. So just to illustrate that they definitely operate differently than vertex colorings. Okay, and then the edge chromatic number is just the minimal k, so that there's an edge coloring with k colors. So the edge chromatic number is min k, such that there exists an edge coloring, let's say of G with k colors, and it's denoted chi prime of G. This is pretty common in graph theory that when you define a certain parameter on vertices, the corresponding parameter on edges uses the same notation with a prime there. It's just a kind of a convention there. Okay, and so in these 3 examples, actually, we also found the edge chromatic number. I mean, so this one was clearly 6 because you needed at least 6 colors because this vertex here saw 6 edges, so all the 6 had to be different. They were all adjacent, and I exhibited one with 6. The path clearly has edge chromatic number 2 as well. You're never going to have edge chromatic number 1 unless none of the edges touch each other, and you just have a bunch of isolated edges. So you need at least 2, and I exhibited 1 with 2. And then here, this has 3. Clearly, you can't do with fewer than 3. A triangle is always going to require 3 because a triangle is 3 edges that are all pairwise touching each other. So you can't repeat a color among those. Okay. All right. And the star here actually immediately leads to a very simple observation, is that the edge chromatic number of G is always bounded below by the maximum degree of G, right? You have a vertex of max degree, you're going to need at least that many colors no matter what. Okay, so that's already something pretty different and interesting compared to the vertex chromatic number, because Brooks's theorem for vertices says that the chromatic number of a graph is at most maximum degree, except for a few exceptions. And the edge chromatic number is going to be at least delta, right? So there's a high probability that these 2 things are very, very different from one another. And let me give the first theorem. I'll zip through this though, because the second theorem's somewhat lengthy. Well, I think we'll be okay. But so the first theorem here is by Koenig. And this says that if G is a regular, so all degrees are the same, bipartite graph, then the edge chromatic number of G equals delta of G. Okay, so if you're regular and bipartite, then the number of edge colors you need is exactly equal to the maximum degree. And in this regular graph, the maximum degree is just the degree, right? Every vertex has the same degree. So it's just the regularity of the graph. And to prove this, we just need to show an upper bound of delta G, because we automatically have a lower bound of delta G by this observation. It's always a lower bound on the number of colors needed. So let's exhibit an edge coloring of G, my regular bipartite graph, using only delta colors. Okay. And the proof is actually very simple here. You can formally set it up as an induction here, but I'm just going to argue through it here. We know something about regular bipartite graphs. We proved something in one of the homeworks. Does anybody remember? What substructure can you find in a regular bipartite graph?
A perfect matching?
Yeah, exactly, Ethan. So it has a perfect matching. Okay, great. Grab perfect matching and color it color 1. So, and remove it. So find a perfect matching in the graph, remove the edges of the perfect matching after coloring them color 1. What does the resulting graph look like after you remove a perfect matching? It's still bipartite.
Bipartite graph.
Yeah, and it's still regular. Okay, so G prime, that's the result, is regular and bipartite. So what are you going to do with that one? It has a perfect matching as well. So color a perfect matching and remove it. Okay, say color 2. And just repeat this process. Every time I color a perfect matching, remove it, I'm left with a bipartite regular graph, and I can find another perfect matching, color it, and remove it, and so on. And do this delta of G times. Right? Each time the max degree, all the degrees drop exactly by 1. And so eventually every single edge has been removed, and I use delta plus G colors. So I produce the coloring. Okay, that's the end of the proof, right? It's very, very simple. Okay. This leads to another observation. We won't use this, but what does a color class look like? So a set of edges of the same color form not necessarily a perfect matching, right?
Independent set?
Yeah, they're an independent set of edges, right? That so form an independent set of edges, right? They're edges that aren't incident, or actually we an independent set of edges is a matching, right? It's just a matching. So right, a matching is a collection of edges that are pairwise non-incident, and so each use up 2 vertices. They don't necessarily span the graph. In this example in Koenig's theorem, we did each of the matchings, each of the color classes saw every single vertex. But in general, that doesn't have to be true, right? If we scroll up to these examples here, maybe especially if I add like one more here, like if you look at the edges of color 1, they see these vertices, they see all the vertices, but the edges of color 2 only see these 4 vertices and not all 6. Right? There's no reason it has to see everything. Same with this one here. Edges of color 3 see this and this vertex, but edges of color 2 see everything, this one and this one. Edges of color 1 see everything, this and this. And here, edges of any color class don't see all the vertices by any means. Okay. But the point is, edge colorings are closely related to matchings. Okay, so asking for an edge coloring of a graph is asking for a way of decomposing the edges into a bunch of matchings that are pairwise edge disjoint. Okay, that's just breaking it down into a bunch of matchings. And actually, Koenig's theorem is really nice because it says that if you're a regular bipartite graph, I can decompose into perfect matchings, not just any old matchings, but perfect matchings. Okay, which is nice. Okay, so now let's say the big theorem of edge, the theory of edge colorings, which kind of like closes the lid on the subject. To a degree, there's other things we can say, but this is Vissing's theorem. And let's add a if statement here, even though we don't actually know it, so need it. So if G is a simple graph, then Okay, remember, simple means no loops and no repeated edges, no multi-edges, okay? Multi-edges, you can still find a proper edge coloring of your graph with multi-edges. This theorem just has to be altered to make it doesn't quite work in that case, okay? So a simple graph is just ordinary graph we've been working with in the class the whole time. Then the edge chromatic number, I'm going to include this in the theorem, is bounded below by the maximum degree of G. We already observed that, that's just immediate here. And it's bounded above by the maximum degree of G plus 1. Okay. Simple theorem. Look what it says. The edge chromatic number can only take on one of two values, either its max degree or one more. That's it. Okay. So in some sense, edge colorings are kind of like less rich than vertex colorings. Vertex colorings can go all the way up to max degree plus 1, or most of the time just max degree, but they can take on values from 2, 1, 2, anywhere in between, and have all kinds of rich structure. But an edge chromatic number, so edge colorings, you only need one of these two options for the number of colors. You can use more colors, of course, but the minimum is always one of these two values here. Okay, and actually this yields something interesting. Graphs, every simple graph can be classified whether it needs delta plus 1 or delta colors, right? Every one falls into one of the two categories. And we call these, it's not very creative, these are called class 2 graphs, and these are called class 1. We won't talk about this much, but you can classify all graphs, simple graphs, by these two categories. In general, it's an NP-hard problem to determine which class you're in. Okay, so if I ask for a general algorithm to decide whether you need delta or delta plus 1 colors, algorithmically that's difficult to do. So there's no simple theorem characterizing saying, hey, you need delta plus 1 here and delta here. We just have theorems like the one above where, oh, under these specific circumstances, you need delta. So regular bipartite, these are class 1. But a general characterization of whether you're class 1 or class 2 is sort of out of the question for now. Okay. So in order to prove Ising's theorem, we simply need to produce an upper bound of delta plus 1. I need to find a coloring of every edge coloring of every graph that just uses delta plus 1 colors. Okay, it's as simple as that. So we'll just produce it. We'll use a strategy we've used often in this class for planar graphs and for Brooks's theorem. We'll start with a minimal counter example, and then remove an edge. And so we're going to suppose everything but that edge is already colored using delta G plus 1 colors and figure out a way to color that edge. Okay, and we'll look at, hey, if this edge can't be immediately colored, what's going on with the rest of the graph? Okay, okay, so the proof is as follows. First, let's just put big delta equal to delta of G so that I don't have to write delta of G every time. Okay, so that's the max degree. And let G be a minimal counter example. Okay, let's be careful. Edge minimal counter example. Okay. What this means is that G minus any edge UV is delta plus 1 edge colorable. Okay. Even if removing this edge drops the maximum degree, then this one would be actually delta minus 1 plus 1 colorable, and that's just delta colorable, which is therefore delta plus 1 colorable still, right? Even if this dropped you down to a smaller category, it'd still be colorable. Okay, and UV is just an arbitrary edge, and this is how we're going to work with that arbitrary edge. Okay, so I want to recolor that. Okay, so the goal is recolor edges of G minus UV so that color becomes available for UV. Okay, and a lot of this proof I'll illustrate through picture here, writing it out in words, which it's actually not in the notes now. There is a version of this in the Diestel book, the yellow book. But anyway, it's much easier to illustrate through picture here. Okay, so there's a super important, like the key observation. This key observation to the proof here is that our palette of colors is delta plus 1, and the max degree is delta. So what that means is at every single vertex, there's a color that doesn't appear. Okay, so at each vertex, there is an unused color as, okay, delta plus 1. Okay, as there are more colors than the maximum degree. There's just one more, but that's fine, right? If you look at a vertex, say this vertex has maximum degree, delta, how many colors can this vertex see? Delta, but there are delta plus 1 colors. So there's definitely a color that's not used on that vertex. Okay, and so the strategy to this one here is to find those unused colors and somehow get my unused color, how to put this, to get the right unused color put onto the edge UV here. Okay, so let's start drawing things and giving the names to vertices here. Okay, so I'm going to draw my edge here U, and then let's draw a dotted line V. Okay, so this is the edge that isn't colored yet, and I want to figure out a color for it. And we're going to be able to make observations about the graph due to the fact that this, at the moment, I don't have a color available for this edge here. Okay, and the end of the proof will be that we can produce a coloring, which I've said over and over again is my least favorite type of contradiction. But if you want, you can easily change this proof into an algorithmic one where you just say, this edge is uncolored, here's what you do to color it, and then find the next uncolored edge, and here's what you do to color it, and just repeat that as many times as there are edges, which will produce a coloring. But anyway, makes the setup a little bit easier. Okay, so what I'm going to do here is, so denote, what I'm going to do is the edge color that's not used at a vertex, I'm going to record it by drawing it in a red circle. Okay, in like this red circle at each vertex. Okay, so remember, each vertex, there's a color that hasn't been used there. Okay, so at vertex U, there's a color. Actually, in principle, there's 2 unused colors at vertex U here, because the max degree, this edge is not colored as well, but we don't even need that. So let me just draw it in red here. So at U, let's call color A0 is the unused color at U, right? There's an edge of not used of that color. Okay, so my first thing would be like, hey, why don't I just color this edge color A0? By the way, let's call these C, not A. I don't know. C is better, right? C for color. C0. Okay. So you tell me, why can't I color this edge with C0 and be done with it? What's the situation that would prevent me from doing that?
There's an edge adjacent to V using C0.
Exactly. So I guess I'm going to draw this for now, but it's gonna get a little out of hand. There's an edge on V that that uses color C0. Thanks, Ethan. Right, everybody see that? Otherwise, I could put C0 here and be done with it. So this edge color has to appear there. Okay. All right. So yeah. Now at V, there's an unused color. Right? V is also a vertex. V has an unused color. Let's call it C1. Okay. Notice necessarily C1 is different from C0 because it sees C0. So C1, the color it doesn't see, is something other than C0. Okay. So C1's the color missing at V. Okay, great. So then I'd say, well, why can't I color this edge with color C1? Basically the same reason. You better see an edge of color C1. So now I'm going to draw that. I wanted that to be in black. So, hey, what? Okay. So this has color C1. So I draw C1 on the edge there. Okay. Now this vertex V, I'm going to rename it V0 just so I have like something consistent here. Okay. So so let's put, I don't know, put V equal to V0. Okay. I'm going to enumerate the neighbors of U. I'm going to call them V0, V1, V2, V3, V4, and so on. Okay. So this gives me vertex V1. That's the vertex adjacent to U along edge color C2. I know edge color C2 exists adjacent to U, because if it didn't, I could use color C1 on the edge UV and be done. Okay. All right. So we're going to continue this process here. Now look at this vertex here. This is also missing some color, right? That color, let's call it C2. Okay. Now we'll get here in a moment, but for now, let's just pretend that C2 is different from all the previous colors that I've given names to. Okay. It's definitely different from C1 because C1 appears here, and so C2 doesn't appear here. That's not the color. C2 though could be C0 for now, right? But let's just pretend it's different. It doesn't matter until we get to the end of the proof. Okay. Okay. Now, what I want to argue here, I'm going to draw these things and then erase them, so the notes may not be terribly useful at the end here. But now what I'd like to do is do what the notes I'm working off call like downshifting. What I'm going to do in this case is I'm going to replace C1 with C2, and then I'm going to put C2 here. No, I'm not. And then I'm going to put C1 here. Okay. This would produce a coloring of the graph, right? Unless something. So just hold your suspension of disbelief for a moment here. C2 is not here, so let's put it on this edge here. And if I put it on this edge here, C1's now been removed. And then C1 is safe to go here because it's not here. And it was on U, but I removed it. So now C1 became safe here. So C1 is safe to color here if C2 is safe to color here. Why can I not do this though? This flipping strategy here, what would prevent me from doing that?
There's another edge from U.
Yeah, U might have had C2 on it, right? So there might have been an edge. So I'm going to erase these blue edges and say, hey, I can't do that thing. Why can't I do it? Because there's another edge coming off of here that has color C2 on it. And then it'd say, oh, if I cross that out and try to color it with C2, this is not fair because C2 is already appearing here. Okay. Now it's C2, color C3 doesn't appear. Right? For now, again, assume C3 is different. And then let's try to do the same strategy again and say, okay, C3 is not here. Color this with C3. Then this becomes safe to color with C2 because it's no longer there. And then this becomes safe to color with C1 because C1 is no longer there. Right? So I try to employ the same strategy, but this doesn't work because there better be an edge coming out of here with color C3 on it, right? And so on. So I'm going to repeat this process and basically just keep saying that, hey, and let me draw a picture here that now we figured out here that, okay, it's the same picture, but so here's V0, and we now found V1 that has C1 on it, and then V2 that has C2 on it. And then you keep going and you get, I don't know, let's say like VK that has CK on it. And I can just keep doing this procedure here. And this was missing, so this is missing C1, which gave rise to an edge of color C1, otherwise I could shift. And this gave rise to color C2, otherwise I could shift. I mean, this was missing here, which has to be here, otherwise I can shift. C3, ... And then here was missing VK plus 1 in principle. Okay, and I can just keep repeating this process and finding a new vertex which uses this unused color. One of two things has to happen. Either this procedure just stops, because like there's only a finite number of colors, right? And so like, and finite number of edges, right? So one or the other of those two things, there's three options here. Either I run out of edges without repeating a color, or I run out of colors without repeating a color, or I repeat a color. Now, what do I mean when I say repeat a color? I mean that the unused colors, there's eventually I might get a repeat of one of these, okay, of the unused color. If I get a repeat of the unused color, that's the interesting case. That's the thing I have to deal with. If this procedure just eventually terminates and says, oh, I get to here and say there's actually no edge coming out of here that uses color VK plus 1, like if I don't have that, then I can shift all the way back. Right? Remember, I always said that why can't I do this blue shift? Because C3 appeared on an edge. Why can't I shift from here? Because C4 appears on an edge. Why can't I shift? Because C5 appears on an edge. That procedure can't go on. You can't just keep saying that goes on forever. There's only so many colors. There's only so many edges. So what happens is there's a repeat. Otherwise, we can shift. Okay. So obviously that's hard to put into words on the canvas here, but I hope you guys follow the idea there. Okay. So this implies that eventually we reach vertex, let's call it VL, that does not, okay, that is missing color, let's say CK. Let me put that in red just to be consistent here. That appears among colors C0, C1 up to CL. Okay. I'll illustrate this to make this a little bit easier to follow, but the point is, maybe I can draw it here. I'll draw it again in a moment here. So dot, 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 and then I continue on, and eventually I reach the edge VL here. And why is this VL? Because color CL was here, and then the color that's missing here is VK. And VK was something that already happened before. Okay, right. Remember, we can't just keep introducing new different colors here forever. Eventually we either stop and we can shift everything back, or we reach a repeated color, a repeated missing color. You can't achieve a repeated color on the edge, right? Because all these colors appear here. Okay, so let me redraw this picture because these are not actually the indices that I want. Okay. In the proof of this, I'm just have to redraw this picture like 3 times, but there's nothing to it but to do it. Okay, so here's U, and then we've got the special vertex V0, and then so how did I draw these consistently? Get the repeated color. Okay, and then let's draw a couple of these. So there's V1, V2, and then this just goes on for a while, and then we get to, this is going to be VK minus 1. And then we continue on some more, and then we reach VL. And here's where things get interesting. Okay, so let's write down the missing colors at each of these points here. So the missing color here was C1. Missing color here was C0. Then this was C2, C3. The missing color in VK minus 1 is CK. And then VL was the interesting vertex where we repeated a missing color. We also had CK was missing there. Okay. And just to fill in the picture, let's write down the edge colors that we know as well. This was C1, right? The missing color of C1 had to be there. Otherwise, we could do the shifting. C2, this is CK minus 1. And this would have been CL on this vertex here. And the CIs are all different. I mean, they have to be. This is a proper edge coloring at this moment, right? So the CI colors have to be different. But then the procedure here would say, oh, why can't I do the recoloring strategy? Well, because CK appears somewhere, right? There's an edge that has CK, but that edge already exists. Actually, it's not drawn here, but there's VK here with edge color CK on it. So this shifting here would not work, right? I can't just shift here, even though I got this repeated CK. That's already an edge color appearing on this one here. So I can't easily shift. Right, does that make sense? Maybe I can draw this one in as well, just to illustrate. And that's why this case is still problematic. So here's VK. And the color on VK is CK. And so if I said, oh, replace CL with CK, and then replace CL minus 1 with CL, and try and shift there, I run into this case here. Oh, wait a minute, CK is here and it's here. Like, how do I resolve that? You can't shift in this picture here. However, you can. You just have to do an additional shifting. Okay, so let's what I want to produce here is a walk on colors CK and C0. Okay, so I want to walk along edges of colors CK and C0. Okay, so where do I start here? Let's say let P be a well, it's a path in edge colors let me get the order right here. A0/AK. Oh yeah, okay. I have to, okay, sorry. Let me write this, starting from A0. Sorry, starting from, yeah, okay. Edge of color A0 at vertex VL. Okay, so I got ahead of myself here. Ethan, go ahead.
No, you changed A's to C's.
Oh, thanks. Yeah, that's the first problem. Yeah, definitely. Yeah, colors, those colors. There's another problem here. Like I got ahead of myself here. What I want to do is start at this vertex and walk along edges of color A0, AK, A0, AK, A0, AK, A0, AK, like red, blue, red, blue, red, blue, red, blue. But is there even an edge of color C0 at VL? Like that's not in my illustration here. So I want to convince you that there is. Otherwise, you can do a swapping as well. Okay, I want to stay on this picture here because I will have to draw this picture a couple more times, but I don't want to do it more than I have to. So let's put claim. There is an edge of color C0 at VL. And I think if there's not, we can do a shifting trick here. I actually don't remember. Let's try then. I mean, so a lot of this proof just comes down to like figuring out which shifting will work here. Let's try if this is, so if C0 is missing at VL, then we're also missing C0 here, right? I'll put that just to be consistent there. And so my strategy will be, okay, obviously if C0 is missing on this edge and it's missing on this vertex here, I can color this C0. And now, can't I just change this to CL and be done with it without shifting anything? Anyone see an issue with that? C0, there is an issue with that. There might be a CL edge here, right? I can't just, so I do have to go through I need to get C1 on this edge here because C1 is safe here, okay? Yeah, okay, good. I'm actually glad we saw that. So what I'll do then instead is, yeah, we'll just go backwards, okay? Let me draw in one extra edge here. Oh. So this is VL minus 1. This had color, no, this is missing color CL, right? That's why CL was there, because CL was missing here. And then this was the first repeat, okay? So then what I'll do here, the edge color, CL is not on this one, and this no longer has CL. So this becomes CL. Why are my colors not cooperating? This becomes CL, and then I just drop by 1. This CK becomes CK minus 1. This CK minus 1 becomes CK minus 2. And this C2 becomes C1. This C1 becomes C0. Uh-oh, that's a problem. And this becomes C1. But this obviously doesn't work either, because there's C0 and there's C0. What did I do wrong? What did I do wrong here?
I think you're adding one rather than subtracting one.
Yeah, did I go backwards, Ethan, here? Yeah. Okay, let me undo this. Yes. You're right. I'm adding one, right. This has CL on it, and the edge before it has CL minus 1, and it doesn't have CL. So it became CL, and then CK becomes CK plus 1. They go up, right? L minus 1 went to L. K minus K went to K plus 1. CK minus 1 went to CK. C2 went to C3. C1 went to C2. And then this, which is uncolored, can safely become C1. C1 will always be the goal on this edge here because I know that C1 isn't here. So it's the only safe edge color, potentially. And it wasn't safe because C1 was here, but if I can get rid of C1, I can put C1 there. And to get rid of C1, I need to get rid of C2. To get rid of C2, I need to get rid of C3 and so on. Yeah, so the edge colors go up, excuse me. Okay, but this was in the case when C0 was missing from VL, then I could say, oh, just put C0 here and push up everything. Okay, so this claim is then proved. There better be a C0 edge coming off of VL. Okay, all right. Yeah. I don't want to draw this picture again, so I'm just going to go get rid of the blue stuff here. I don't even need that edge. And what this means is that C0 does appear at VL. So let's draw that edge. Actually, I'm going to use a new color for that anyway. So this edge has color C0 on it. Okay. Now, let's do this part here. I'm going to create a path that alternates between colors C0 and CK that starts from an edge of color C0 at vertex VL. So this edge definitely exists. And I start here, and CK doesn't appear on this side here. So if this path can be extended, it's extended from the opposite side of CK, right? It could go here and get a CK, and then it could get another C0, and then another CK, and so on and so forth, right? Does everybody see I can try and build up this longest path, okay? So this is a longest. Are there options for this path? Is there any point at which I'm like here and I can go to CK or to do a different CK? No, the edge coloring is proper. So when I reach a vertex here, it incomes from a color of C0 or CK, and it continues on from the opposite color, and there's no options. Or it's terminate, right? There might not be another. It might not be able to continue it, but this is a unique path. Starting from here, there's only one way to walk along edges, alternating in these two specific colors. And in particular, it goes away from CK. Okay. So I mean, away from VL, this first repeat. So it looks something like this. Okay. And then the remainder of the proof is 3 cases of case analysis, depending on where this green path ends. Okay. So it does terminate eventually, of course, right? The graph is finite. And the question is, where does it terminate? And this will be reminiscent of like Kempe chains or something like this. We'll be able to assume it ends in the one place that prevents us from doing the appropriate alternating trick. Okay, because what I want to keep in mind is the edge colors on this path here, I can swap them, right? Look what happens if I swap the edge colors on this path here with each other. Then this becomes CK, C0, CK, C0, and so on. This can never cause me a problem in terms of the coloring of the graph, because this one, which was CK, became C0. Why would that be a problem? If this newly colored edge saw an edge of color C0 already, right? You can't change it into a color that's next to it. But any edges of color C0 that are next to this edge became CK in the swapping. They were on this path, right? So if you take an alternating path in 2 colors, you can swap the 2 colors along that path safely, always. You can't get yourself into trouble. So we have that additional swapping strategy at our disposal, okay? And moreover, this one that's C0 becomes the starting of the path becomes CK. This is also safe because VL doesn't see color CK, right? That's how we started off the whole thing. Color CK isn't here. So this becoming CK can't be a problem from this vertex's perspective. And it can't become a problem for this vertex's perspective because there was a CK, but there isn't anymore. And there's no other CK to interfere with it. Okay? That's just repeating the same argument again, that the swapping the path is safe. Okay, so we have to examine 3 cases, and I'm just going to redraw this picture for the cases here. Okay, so case 1, P ends in vertex. I don't remember here. Okay, no, let's see, not even ends. P uses vertex VK. All right, let's go back up and look at the picture here. VK, really? Yeah. Okay, so the green path, P, alternates C0, CK, C0, ZK, and eventually comes here. Okay, we're looking at case 1 now here. So it comes into this thing here. If it comes in and hits VK, what's the color of this green edge then? Yeah, Ethan, I can read your lips there. It has to be C0, right? Because here's an edge of CK, right? So it can't enter that vertex through an edge of CK. Oh, okay. I guess it can. If it could come into U and then go across CK and then go out C0. I guess that's possible. But that's fine. The point is the green path includes all these edges here. It includes an edge of C0 coming out here and includes an edge of color CK over here. And either this one ends up touching here or, oh no, it can't. Haha, nice. Yeah, what I said is wrong. Can it enter into U via an edge like this? No. Why not?
Because C0 is free on U.
Yeah, U does not see color C0, right, by definition. So yeah, so what I said earlier was impossible. You can't enter into U on this green path, except this way. So you go alternate blah, 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 dot, 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 dot. Then you come in here, you go along C0, and then you go along this CK, and that's the end of the path, right? The path ends at U. Okay, it started here and ends here. In particular, this path is not a cycle, right? I mean, in principle, the path could be a cycle, right? And that could be problematic, but this is what it looks like. Okay, so this is actually case one, what I've illustrated here. And here, what's the swapping trick here? Here, I mean, we can probably read it out immediately. I know that we're going to swap the path. So this becomes CK, and this CK becomes C0. Okay, and that's safe. So all the green needs to become blue. And then I'm also going to shift probably up, the usual up. Now, edge color CK no longer appears incident to U, right? Because it was here and I changed it to a C0 by doing this path swapping trick here. So now let's change this to CK, change CK -2 to CK -1, change C2 to C3, change C1 to C2, and then put C1 there. Right, the usual strategy, I want edge color C1 there. Why was I able to do that? Because I got rid of CK over here. How did I get rid of CK? By alternating along this green path. Okay, and this green path's existence, let's just back it up a little bit, came about because VL repeated the non-use of color CK. Okay, I know it's a lot to hold in your head, but like anyway, we got the green path. The existence of the green path ending here in case one allowed us to finish. Okay. But that's not the only way the green path can end. So let me undo this again. I guess I don't have to illustrate this picture a bunch of times. Okay, is this one fine? Right, we were able to get rid of CK, turn it to a C0, which is safe because it's not here. And once we did that, we could like upshift the indices of these colors here. Since CK is no longer here, this can become CK. Since C2, C3 is no longer here, it became C4. We can put C3 here. Since C2 no longer appears here, we can put C2 here. And since C1 no longer appears here, we can put C1 there, finishing the proof. Okay, now let's look at another way that green path can end. How many? Okay, all right. Now the green path could also end. What's another interesting case here? So case 2. P uses vertex VK -1. Okay. VK -1. Is that like the same? So if the green path uses vertex VK -1, it enters into it on an edge of color C0, not CK, because CK isn't there. And moreover, it terminates there, right? Remember the previous came in here on C0 and then went along CK and then terminated there. This one terminates here because there's no CK to extend it by, okay? In this case, okay, I don't remember the shifting, but I know that in each step you shift the path. So let's just shift the path first. So this becomes CK. And now, then here, we should be able to put C0 on this vertex, on that edge there. Right, C0 is no longer appearing at VK -1, and it's not appearing there. And then we can do the same thing. I'll draw an additional edge here. Here's edge VK -2, and it has color CK -2. But then I can shift up. this become, since ck minus 1 is no longer used, this can be ck minus 1 dot dot dot. This c2 becomes c3, this c1 becomes c2, and this becomes c1. Nothing too different there either. Okay, now the final case. The final case is that this green path just terminates somewhere other than this vertex and this vertex. It might terminate in one of these n vertices, or it might just terminate somewhere entirely different in the graph. Okay, we don't actually care. Okay, so the final case, P avoids vertex. What vertices does it avoid? It avoids VK because we dealt with that. It avoids vertex VK minus 1 because we dealt with that. There are also a few other vertices it automatically avoids no matter what. It avoids, therefore, U. How was the only way that it could use U? That was in coming in this edge here. But we said it avoided VK, so it necessarily avoided U. I actually don't remember the significance of this, but let's look real quick here. We're almost at the end here. This last case is easy too. U and then, oh, and actually what this, I wrote that it avoids VL, but that's nonsense. Okay. And does not end at, let's say, VL. Just go back up here, right? It can't end at VL. Oh yeah, before I said it in principle could be a cycle, but it actually can't be a cycle, right? It leaves on color C0 here, but in order to be a cycle, it have to enter back into here on edge color CK, but CK does not appear here by definition. So actually the green path truly is a path. Okay, all right. So let's look at the last case here. Oh, I should have erased first, but it's okay. So this is getting rid of my case below. Yeah, that's okay. Just bear with me with all the clicking. Come on, blue should start disappearing now. Almost. Oh, yeah. There's a queue in the undo, right? It can only go so long. So just I'm gonna erase a little bit here. Okay, we're still gonna shift these, but we just decided now we're in the final case with the. Oh man, it's terrible. Let's try to do a little surgery here. Fine. Okay. CK minus 1, and this was C2, C1. And actually this, I don't need this edge here. I added this one just for the previous case. Okay, so it doesn't say case 3 anymore, but case 3 is that this path just like peters out somewhere. Okay, and this vertex here, it could like come into there, for instance. It maybe, but that's not going to matter. Okay, if it came into there, this could be C0 or CK, right? V2 doesn't know anything specific about C0 or CK. Okay, so you can imagine this one if you like. But I'm going to swap the edge colors here this way. And then what I want to do is, what do I want to do? I mean, this is actually a good exercise for you guys if you see it.
Yeah, it's basically the same as the very first one we did.
The first one?
Swap the path, and then there is no longer a C0 next to VL.
There's no longer C0 next to VL?
If you swap the path.
Oh, very good. Yes, I see what you're saying, Ethan. Yeah, okay. So I don't even necessarily need to draw it, but remember early on, we argued that there has to be a C0 here. And if there was no C0 here, we were able to do the swapping by turning this to C0. Let me do that in blue just to be consistent. Turning this to C0 and then shifting and then, did we have to shift? What did we do? Then we shifted
everything up.
We shifted everything up, right? So this edge here, let me add it. So this VL minus 1 was CL, and it was CL minus 1, and it didn't see CL because now it becomes CL, and this CK becomes CK plus 1, and then CK became CK, this became C3, this became C2, and this was able to do C1. And this was safe. And maybe in some sense, this would have been the best thing to do for the first case, right? Or the second case. because it was the same argument, right? We freed this up from C0, and we showed when it was free from C0, there was a way to do it. And the only ways not to be able to do this is if this green path terminated here or here, and then it interfered with this, because it's like, hey, I can't change this to CK because I changed this C0 into a CK, which interfered. But that doesn't happen in the third case, and so we're safe. Okay? Yeah, thanks for that, Ethan. And so that ends the proof, okay? Again, in the notes, this is not going to be very illustrative because I erased and redrew, but I mean, that's the advantage of being able to do this in a lecture. So there was a way to swap this no matter what. And this edge can receive color C1 in any one of these cases, which formally is a contradiction to the minimal criminal setup we had here, but you don't actually need that. You can just say color as much of the graph as you can. As soon as you stop, you have an uncolored edge. So you just have a subgraph and one uncolored edge. So just perform this procedure on that to color that edge, and then repeat for each uncolored edge until every edge is colored, okay? And so just to remind you, where did we use the observation that the degree and the number of colors differed by 1, that we had 1 more color than degrees? Because that was the key information we knew about the graph here.
There was a missing color from.
Yeah, exactly, Ethan, right? It was this key observation. It was the existence of these red circles. Every time we talked about the existence of these was due to the fact that we had 1 more color than the max degree, right? So those always existed. If you don't have that, then you can't talk about these missing colors, and you can't do this. This proof completely breaks down utterly, right? And so you'll never improve to delta plus just delta as an upper bound, okay? But of course, there are graphs that require delta plus 1 colors, so you couldn't improve it to that in general. Okay, let's stop there.